Welcome back. Day 2 of our discussion of momentum. Let's take a quick review of what we talked about yesterday. We went in the back, I think, when we began and looked at the idea of momentum in different objects and was pretty much able to determine, based on what we were able to observe, that momentum was directly proportional to not just mass but also velocity. Came up with a formula essentially just relating the two, the product of the two, which makes them directly proportional. It said momentum is just the product of the mass of the object and the velocity it's moving. It's a quantity that Newton used to describe all of his motion. It's a vector quantity, and it's the direction of the momentum vector is the same as the direction of the velocity vector. The units of momentum are just kilogram meters per second. And today we'll see another way of writing that. Momentum can be transferred from one object to another. Newton said momentum is conserved in a transfer in any closed system. So the amount of momentum you have in a system remains constant, even though it could be transferred from one object to the next. The experiment we did yesterday was the ball rolling down the hill and transferring its momentum to a block, which caused the block to move away. Okay? And we said that the momentum is conserved, the momentum of the ball ends up going to the momentum of the block, and if it gives it all its momentum, you can say before collision, whatever momentum the ball had became the block's momentum after collision. We also did our example with the deer, with the impact on a deer, or the momentum of the system, the car, before collision. Okay? The momentum of the entire system, the car actually and the deer in this case. The deer has no momentum, the car has momentum, the deer is not moving, the car is. So the momentum of the car plus the momentum of the deer is the total momentum of the system, right? And we quantify those things by just filling in our numbers and came up with a total momentum of the system of 25,500. And because of Newton's rules about momentum conservation, we knew that after collision, the total momentum still had to be that same number. But now, since the deer happens to be moving, some of the momentum of the car now is with the deer. So therefore, since we only have 25,000 to distribute, we're going to lose some momentum in the car because the deer has picked it up. We can actually calculate then the new momentum of the car, or the velocity in the car in this case, by taking the total system, taking the momentum of the car, plus the momentum of the deer, which we can plug numbers in for, and calculate that in fact the car had to slow down because it lost some momentum to the deer. Total, again, remained 25,500. This type of collision, where the masses in the closed system remain separate before and after collision, is called an elastic collision. Okay? We also looked at an inelastic collision. And we didn't define this yesterday, but now we can, as saying that the masses combine after collision. The masses combine after collision. Okay? So what we had, though, is the same momentum before was 25,500. It's still the same after. But now it's, again, spread over both objects, the car and the deer. But since they're both moving at the same velocity now, okay, what's going to happen is that the 25,500 is spread over the mass of the car times its velocity, plus the mass of the deer plus times its velocity. But since the deer is stuck on the car, they're both moving at the same velocity. So we can work down through the math and solve that the velocity of both car and deer is 15 meters per second. I'm going to take this to the back and maybe give you another example of elastic and inelastic collisions. Welcome back. I've done another demo here to show elastic and inelastic collisions. And instead of objects of different mass, I've actually come up with two objects of the same mass. They're these collision carts, momentum carts we call them, and there's two of them. And they're sitting on this track, and it's a fairly low friction, so I'm trying to keep the system as close as I can. The system being the two carts. Now there is friction and vibration, and it's attached to the table, which kind of is outside the system. We can transfer momentum that way, but right now I just want to show you the real basics of this, of transferring momentum. So what I'm going to do is I'm going to take this cart, which will have no momentum because its velocity is 0, and slide this cart into it. And I'm going to try to get this cart transfer all its momentum to that cart. And watch what happens. Okay? This cart stopped and transferred all its momentum to that cart. And since the carts are the same velocity, this lost all its momentum to this cart, so this cart moves away at the same velocity. Let me show you again. Okay, that's an elastic collision, isn't it? Because the masses of the two carts remain separate. And the reason for that is that these carts have magnets in the front of them which cause a collision without any physical contact. So that's how we can get that to work, and it works the same the other way. Okay, this transferred its momentum to this cart moved away at the same velocity. That's an elastic collision with the same mass. Now I can change one of these carts out to one that doesn't have the magnet in it. And what I can get to happen is I can turn it into an inelastic collision because the carts have Velcro in front of them. So now what will happen is that this cart will come across and contact this cart, but the masses will combine because the Velcro will hold the carts together. Now, how will the velocity of both carts compare after collision to the velocity before? Well, if the masses are the same, what happens is this momentum of this system now is spread out over twice as much mass. So you would expect the velocity should be half of what it was before. Okay? Because now mv, then we have twice the m, so we should have half the v after collision. Here we go. And that's exactly what happens. The velocity, now we're not able to quantify it. Actually, we could if we could read these numbers while we're doing this. But we can clearly see that the momentum slows down. This is analogous to our deer and the car situation that we looked at yesterday. The deer added mass to this, the deer's mass combined with the car's mass, so the velocity of both went down. Now the mass of the deer was 1/7 out of the car. But here when the masses are the same, okay, the math works out to be half. Now we can fiddle around with this a little bit and increase the mass. So what I could do is I can triple the mass of this cart. Okay? Now it still has no momentum, even though it has 3 times the mass. However, this cart will have momentum. But when it hits this, now what it's doing is it's spreading out the mass over 4 times, right? This, which would be 1, 2, 3, 4, because each of these is the same mass as the cart. So I've got triple the mass, so it would be 4m. So what should happen is when this hits this, the velocity should reduce to 1/4 of the velocity of the system. Here we go. And you can see that's exactly what happens. This is kind of analogous to a small car hitting a big car or a truck. It does transfer momentum to the object, but the velocity of the system is much lower because there's much more mass that momentum is trying to be spread out over. Now, we could do it the other way and transfer the momentum to this. Now what happens is we've got much more momentum here now because we've got 3 times the mass moving at the same velocity. When it contacts, this is kind of like the deer in the car now. Okay, here's the deer, here's the car with much more mass. So what's going to happen is it slows down, but essentially it keeps moving in the same direction with almost the same velocity. It slowed down probably by about 25% because it picked up 25% more mass, or actually 30% more mass in this case. That's an inelastic collision, isn't it? Well, let's go back to the elastic and watch what happens. In an elastic collision now, the masses are not allowed to combine. So what will happen here is that, watch what happens when this transfers even some of its momentum to this vehicle. Okay? You can see what happened. It didn't even transfer all its momentum because it didn't stop. But this object, which has much less mass, accelerated away, right? Its velocity increased by so much because it transferred that momentum to it. Okay? If we turn it around, this will be an interesting comparison. This would be an inelastic collision between a very light object and a very heavy object. There's your vector quantity. Okay? The total momentum of the system is in this direction a positive number, isn't it? Okay, if we assume this way is positive. The total momentum of the system after collision still has to be a positive number. This is has negative momentum, doesn't it now? Let's go up to the board and see if we can quantify some of these numbers. Okay, welcome back. Let's take a look real quick at the situation we just saw. Again, momentum in any closed system is conserved. Our closed system are two carts. Of the same mass. We'll call it M1 and M2, but they're both the same. This has a velocity. Say it's equal to 1 meter per second. This velocity is equal to 0. It's not moving. This is the total momentum of the system. Okay? If m is equal to, and in this case, 0.5 kilograms, okay? We can quantify the system before collision. Momentum of the system, P system, is equal to 0.5 kilograms times 1 meter per second, which is the momentum of this cart, plus 0.5 kilograms times 0 meters per second, which is the momentum of this cart, because it's not moving. So the total system momentum, in this case, is equal to 0.5 kilogram meters per second plus 0, which is just this. This is the total momentum of the system. So for our elastic collision, as this came over and contacted this came to a stop, and this continued on at 0.5, at 1 meter per second. It had to, because the total momentum of the system had to remain this. In our inelastic collision, this object comes over and contacts this, and they stick together. So now instead of 0.5 kilograms, we have 1 kilogram. Okay? This is before. After, here's our situation. We've got our surface. We just drew our surface as a straight line, so let's make sure we draw it in the same way. We've got the first cart, and it's stuck to the second cart. And it's moving away at some velocity. But the total system momentum has to remain at this number. So we can say 0.5 kilogram meters per second is equal to the total momentum of the system, which is the 0.5 kilogram mass, the first cart, times the velocity of that cart, which we'll call velocity of both because they're both moving off together, plus 0.5 kilograms times the velocity of both again. Okay? Both carts are moving at the same velocity. factoring out v both, you can say 0.5 kilogram meters per second is equal to v both times 0.5 kilograms plus 0.5 kilograms. You can add them together. 0.5 kilogram meters per second is equal to the velocity of both times 1 kilogram, right? Divide both sides by 1 kilogram. This cancels with this cancels out, and I get v both is equal to 0.5 meters per second. So clearly what happens here is the velocity of 1 meter per second is now spread out, the momentum of that is spread out over both carts. So they move off at half the velocity because the mass of the system is now twice as large. Well, it's not the system. They're both moving off now together. So the momentum is spread out over twice as much mass. Now we can throw numbers in here and change it around a lot, but the bottom line here is that momentum is conserved. So if whatever I make the masses, these numbers should still work out. We could talk about a car hitting a fly. You're riding down the road and a fly's sitting there and the car hits the fly. The car has to slow down, doesn't it? Even a minuscule amount, because the fly adds mass to the system. Okay? Even though it has no momentum, it adds mass. And the momentum is now spread out over a greater amount of mass, so there's this minuscule change in velocity. As a result, the car has to slow down a little bit because the momentum is spread out. Okay. Let's talk about ways we can change momentum. Well, if you're talking about a single object or two single objects, the masses really don't change, do they? So essentially, if we want to change momentum, and we've used this term before, delta P, right? Delta means change in. The change in momentum. The masses really don't change. It's really mass times the change in velocity. This is really the only way to change momentum, isn't it? To change the velocity. Okay? Well, we could write this a couple different ways. We can say change in momentum is just the momentum after the collision minus the momentum before collision, which is going to be equal to mass of the object times its velocity after minus its velocity before. Right? These are our changes. So if we want to calculate the change in momentum for any particular object, this is the way we can do it. Just by taking its mass and multiplying by its final velocity minus its initial velocity. Right? You could say final minus initial. Same thing for final momentum minus initial momentum. We'll treat it the same way we did before. But let's take a look at this a little bit more and see if we can kind of come up with another equation. Maybe because when you think about it, in order to change the momentum of an object, you almost have to apply a force, don't you? You have to push on something. If I've got a cart that's at rest and I want to change its momentum, I'm going to push on that cart for a certain period of time. And the cart's going to start moving, so the cart's going to get momentum from that. I think we can get that from here. Let's see if we can. We start out with this again. Change in momentum is equal to mass times the change in velocity. How do we relate change in velocity? Well, if we think about it, if the acceleration of an object is its change in velocity over change in time, I could say that the change in velocity is just the acceleration times the time it was applied to the object. So if I take this and plug it right in here, I can say that the change in momentum is equal to mass times acceleration times the change in time. right? Just plugging in acceleration times change in time in for change in velocity. Well, what is this right here? Newton's second law, F equals ma. This is force, isn't it? So rewriting change in momentum, I can say change in momentum is equal to force times the change in time, just like we said a minute ago. In order to change an object's momentum, you have to apply a force for a certain period of time. This product here is known as impulse. It's called impulse. Impulse causes momentum to change. That's the definition of an impulse. An impulse, or a force for a period of time, causes impulse or momentum to change. It's really, you can see how Newton's law, Newton's second law, actually fell out of this, F equals ma. Because Newton was looking at how momentum changed. And he was able to determine that in order to get momentum to change, you have to apply a force for a period of time. And this is where the second law actually came from, right from this equation right here. Let's try an example with this idea of impulse. Go back to our deer situation, hitting the deer. If we remember correctly, we had the car, which was 1,500 kilograms, moving at 17 meters per second. We had the 200 kilogram deer. Make it a little bigger this time. We had the 200 kilogram deer moving at 0 meters per second. I'm wondering if we could figure out how much force this deer felt as a result of the collision. Well, what we have is we know for a fact from our previous discussion that this was before. After the collision, the deer was moving, wasn't it, at 3 meters per second. This is the elastic collision. Okay, so if we copy this, and then we paste it in down here, okay, after collision, what happens is our deer here is moving off at a velocity of 3 meters per second. Had him. Oh, I don't have them all together. Okay. Let's see if I can highlight him here. Okay, here we go. And he was moving kind of off like, oh, he's all in pieces now, isn't he? That's not good. We're just going to have to redraw on my neck. Let's just have him moving forward this way. At some velocity. So the change in momentum of the deer, delta P, for the deer, is really his momentum after minus his momentum before. We could write it this way as his mass times his velocity after collision minus his velocity before. Right? Mass times the change in velocity. Or 200 kilograms times 3 meters per second minus 0 meters per second, or 600 kilogram meters per second. That's his change in momentum. In order for that momentum to happen, the momentum to change, he would have to have an impulse, wouldn't he? A force applied on him by the car in order to get this momentum to change. And we can say that's going to be equal to 600 kilogram meters per second is equal to the impulse, or the force of the car on the deer times the time the force was applied. Well, let's face it, this impact happens in a very short period of time. So if our delta t is only, say, maybe a tenth of a second, right? Just a tenth of a second is the collision time, the time the car is actually in contact with the deer, and it is a very short time. You can say 600 kilogram meters per second is equal to the force of the car on the deer times 0.1 seconds. Dividing both sides by 0.1 seconds, we can solve for the force on the deer. And it's going to be kilogram meters per second, or kilogram meters per second squared. And you're going to get 6,000, right? 600 divided by 0.1. And what's a kilogram meter per second squared? Well, that's a Newton, isn't it? Okay? So the force on the deer in that situation essentially ended up being about, divide that by about 4.5, that's about 1,500 pounds of force on him, maybe 1,000 pounds of force, which is why you get the injury. Okay? But look at the inelastic collision. This was the elastic collision, wasn't it? Right? The deer is still moving, they're still separate. In the inelastic collision, what happened was, for the inelastic, you notice I've chosen red on purpose, okay? The deer is pasted to the front of the car, and the velocity of the deer after increases to 15 meters per second. Remember, he's moving at the same rate as the car now. So we can look at the change in momentum of the deer. Delta P for the deer is going to be equal to his mass times the change in velocity, or 200 kilograms, which is his mass, times V final, which is 15 meters per second, minus 0 meters per second, his velocity before, because he was at rest. Look how much bigger this change in momentum is for the deer. It ends up being what? 3,000 kilogram meters per second. Okay? 200 times 15. Okay? And if we put that into our impulse formula, okay, this change in momentum, 3,000 kilogram meters per second for the inelastic collision, is equal to the force on the deer times the time over which the force was applied. And again, we're going to assume that the contact time was only about a tenth of a second. So delta t is equal to 0.1 seconds. Now plug this in and see what the force ends up being. 3,000 kilogram meters per second is equal to force times 0.1 seconds. Dividing both sides by 0.1 seconds. This cancels out, and we get a massive force of 30,000 newtons, don't we? Which ends up being divided by 4.5. That's almost 2 tons of force on him. Okay? Almost 2 tons of force on him. And that's why you get the splattering effect that we saw on the deer. All of this discussion of force, impulse, change in momentum is all tied into that same concept that in any closed system the momentum is conserved. therefore the objects that apply the forces to cause the momentum to change, all is conserved. So to summarize, momentum in any closed system is conserved. We looked at the carts in the back. Okay. Now when we get together on Monday, we're going to have to look at momentum changes now as velocity changes direction too. The momentum, we saw that in the back. We really didn't get into it too deep, and maybe we shouldn't today. But the idea that momentum is conserved, the total system momentum before has to be equal to the total system momentum after. We're going to have to start being careful though and causing a direction to be positive. It's still going to be true. In order to get momentum to change, okay, we're going to have to apply an impulse to do it. Momentum change is just mass times the change in velocity. Momentum after minus momentum before is the same as the mass times the velocity after minus the velocity before for any object in the system. Okay, and we derived a formula just by knowing that acceleration is the rate at which velocity changes. We derived a formula for change in momentum, and we called it impulse. Force times the change in time is the change in momentum. An impulse or a force for a period of time causes momentum to change. Right? That's our concept. We applied that discussion to the deer in the car. For the inelastic collision, where the deer ends up moving away, and by the way, let's keep this straight. This ends up being, I think, what, 16 meters per second or something like that from the previous discussion, right? This velocity is slower after collision. The deer moves away at 3. So what happens is the deer's momentum changes, right? His momentum after ends up being, what, 200 times 3, right? His momentum before was 0, or his change in momentum is 600 meters per second, kilogram meters per second, which ends up being, if it's applied over 0.1 seconds to change his momentum, it's a force of about 6,000 newtons for the inelastic collision, or for the elastic collision. For the elastic collision, or inelastic, what happens is the deer's momentum changes a lot more. His velocity ends up being 15 meters per second because it's pasted to the front of the car. His momentum change ends up being 3,000 kilogram meters per second, and his impulse force, the force causing that momentum to change, ends up being about 30,000 newtons. Hence the danger, the damage. Okay. I'm giving you guys a WebAssign over the weekend. It's due Monday night at 11:59 p.m. Hopefully we're able to get the WebAssign if it's due tonight. It's not that difficult. I'll be back on Monday. I'd ask you to continue to pray for the success of Kairos 3771. Thanks for coming.